This code installs the Quandl package, specifically version 3.4.8, using the pip package manager. The user option allows the package to be installed for the current user only, avoiding the need for administrator privileges. The upgrade flag ensures that if a previous version of the package is already installed, it will be upgraded to the specified version. Since this command is prefixed with an exclamation mark, it suggests that it may be run in a Jupyter Notebook environment or similar, where shell commands can be executed directly. The comment indicates that the installation process may take some time to complete. This code imports the Quandl package, which is a library used to access financial, economic, and alternative datasets from the Quandl platform. After the import statement, it prints a confirmation message to indicate that the package has been successfully imported. This setup allows the user to utilize Quandl's functionalities to fetch various types of data in subsequent lines of the code. This code sets the API key for accessing the Quandl service, which provides financial, economic, and alternative datasets. By assigning a value to quandl.apiconfig.api_key, you typically input your unique API key as a string within the quotes. This key authenticates your requests to the Quandl API, allowing you to access the data available through their platform. Just remember that the API key should be kept private and not hard-coded in publicly shared code. This code snippet retrieves financial data for IBM stocks using the Quandl API. It specifically requests data from the Wiki Prices table, focusing on 4 key columns: date, open, high, low, and close. By setting paginate equals true, the code ensures that all available data is fetched, even if it extends beyond the default limits on a single request. The resulting data is stored in the variable data, which will be a structured format containing the requested historical stock prices for IBM. This code snippet is focused on manipulating a pandas data frame. First, it renames the columns of the data frame to date, open, high, low, and close, which is commonly used in financial data to represent stock prices. Then, it resets the index of the data frame, removing the old index and creating a new integer-based index while using the drop equals true option to discard the previous index rather than adding it as a new column. Finally, it displays the last 5 rows of the data frame, which is helpful for quickly inspecting the most recent entries in the data after the modifications. This command installs the Bokeh library, specifically version 1.0.4, in the user's local Python environment. The use of user ensures that the installation does not require administrative privileges and installs the package to the user's directory. The upgrade flag is included to ensure that if there's an existing version of Bokeh, it will be updated to the specified version. This code imports several essential components from the Bokeh library, which is used for creating interactive visualizations in Python. The figure function is used to create a new plot, while output_file specifies the output location for the visualizations, like an HTML file. The show function is responsible for displaying the plot in a web browser or notebook. Column data source is a fundamental data structure for Bokeh that allows you to easily manage data for your plots, making it easier to work with for dynamic visualizations. The components function is useful for embedding Bokeh figures into web applications, and output_notebook prepares the plotting environment to render figures directly in a Jupyter Notebook. The print statement at the end confirms that the necessary packages have been successfully imported. This code snippet is used to prepare for visualizing data with Bokeh in a Jupyter Notebook. By calling output_notebook, it configures Bokeh to display plots directly within the notebook instead of opening them in a separate browser window. This is especially useful for interactive visualizations, making it easier to present and analyze data in a notebook environment. This code creates a Bokeh figure for visualizing historical stock data. The figure is set to a size of 1200 pixels wide and 550 pixels tall, with a title indicating that it displays stock value historical data plotted against time. 4 lines are plotted on the figure, each representing different stock price metrics: the opening price, the closing price, the highest price, and the lowest price, with each line differentiated by color and line width. The opening price is shown in a blue color, the closing price in pink, and both the high and low prices in black with a thinner line width. Additionally, the code customizes the appearance of the axes and labels. It sets the legend to be vertically oriented and labels the x-axis as date and the y-axis as value $USD. The font styles and sizes for both axes are also defined to enhance readability, with bolder and larger text for the axis labels and appropriately sized text for the major labels. The show P function is typically used to display the contents or visualization represented by the variable P, depending on the context and the type of P. This could mean rendering a plot, an image, or even outputting some data structure to the console. The specific behavior of show will depend on the library being used, such as matplotlib in Python for visualizations or other frameworks that support similar functionality. So essentially, it's a command to present or visualize whatever P contains in a way that's meant to be easily interpretable by the user. This code snippet installs the Piston package using pip, which is a package manager for Python. The user flag is used to install the package for the current user rather than system-wide, which avoids potential permission issues. The comment mentions that this installation could take some time and also notes an update related to the requirement for setuptools git when installing FBProfit version 0.5. Overall, the command is focused on ensuring that Piston, a necessary dependency for statistical modeling in Python, is available for use in the user's environment. This code snippet is a command to install the FBProfit library using pip, which is the package manager for Python. The at the beginning indicates that this command is meant to be run in an interactive environment like Jupyter Notebook, where you can use shell commands directly. When executed, pip will download and install FBProfit along with any necessary dependencies. The note that it may take some time serves as a heads up that the installation process might not be instantaneous, depending on your internet speed and system performance. This code snippet imports two essential packages, FBProfit and DateTime. The FBProfit library is designed for forecasting time series data, making it easier to handle trends and seasonality. The DateTime module provides classes for manipulating dates and times, allowing you to work with date-related data efficiently. After the imports, it simply prints a message to confirm that the packages were successfully imported. This code snippet creates a copy of an existing data frame called data to ensure that any modifications don't affect the original dataset. It then filters df_train to include only the rows where the date column has a date greater than January 1, 2008. The tail method is called to display the last few entries of the filtered data frame, allowing you to quickly see the most recent records that meet the criteria. This is useful for inspecting the final dataset used for training in a machine learning context. This code snippet prepares a data frame for use with FBProfit, a forecasting tool. It first renames two columns. Open is changed to a Y, which represents the values to predict, and date is changed to DS, which denotes the timestamps. The next line filters the data frame to keep only the DS and a Y columns, removing any other columns that may have been present. Finally, calling df_train.tail displays the last few rows of the modified data frame, allowing you to verify the changes and see the format is correct for FBProfit. This code sets up a Facebook profit model for time series forecasting. It disables daily and weekly seasonality, but keeps yearly seasonality active, suggesting that the model will take into account trends that occur over a year. The changePoint_pri_scale parameter is defined, controlling the flexibility of the model in terms of detecting changes in trends, with a value of 0.05 indicating moderate sensitivity. Additionally, a custom monthly seasonality is introduced with add_seasonality, where the period is specified as 30.5 days, suitable for capturing monthly patterns. The Fourier_order set to 5 will determine the complexity of the seasonal component, allowing the model to fit more intricate seasonal patterns. Overall, this configuration tailors the model to effectively capture yearly and custom monthly trends in the dataset. This code snippet calls the fit method on a model object, using df_train as the training dataset. It trains the model using the provided data, which typically consists of features and labels, allowing it to learn patterns or relationships within the dataset. After this operation, the model will be adjusted based on the training data, preparing it for making predictions on new, unseen data. This code snippet is executing a forecasting algorithm for a time series model. First, it generates a future data frame that extends the existing dataset by 1 year, with daily frequency, using the make_future_dataframe method. The periods equals 365 argument specifies that the prediction will cover the next 365 days. After creating the future data frame, the predict method of the model is called, which takes this future data frame as input and produces forecasts for the specified period. Finally, future_data.tail retrieves the last few rows of the resulting predictions, allowing you to see the most recent forecasted values. This provides a quick way to assess the ending predictions for the next year ahead. This line of code is calling a method named plot from an object model, passing in future_data as an argument. The plot method likely generates a visualization based on the predictions or insights derived from the future_data, which could be related to forecasting or trend analysis. The resulting figure or plot is stored in the variable figure 1, which can be used later for displaying or manipulating the visual representation of the data. This line of code is using a method called plot_components from the model object to visualize the components of the time series data stored in future_data. The figure 2 variable stores the resulting plot, which typically breaks down the data into its various components, such as trends, seasonality, and any detected holidays or events. This visualization helps in understanding how each component contributes to the overall forecast represented in the model. Essentially, it's a way to gain insights into the underlying patterns of the data you've modeled. This code creates a bokeh figure to visualize historical stock value data. It initializes a plot with specified dimensions and a title, setting the x-axis to display date-time values. It then adds multiple line plots to the figure. The first line represents observed stock opening values for dates after January 1, 2008. The second line shows modeled opening values from a future dataset. Additionally, upper and lower estimate lines are plotted, providing a range of projected values. Finally, the code customizes the appearance of the axes and labels. It makes the legend vertical, sets labels for the x-axis and y-axis with bold fonts and larger sizes, and adjusts the font sizes for the major labels, ensuring that the plot remains clear and visually appealing. The code snippet show P is typically used to display the contents or visual representation of the object P. This function is commonly found in data visualization libraries or plotting frameworks, where P could represent a plot, graph, or some kind of data structure that can be visualized. Calling show executes the necessary procedures to render the output, allowing you to view the information represented by P on the screen. The actual output and format depend on the specifics of the library being used, but the core purpose is to present data in a user-friendly way. This code snippet is using the cross_validation function from the fbprofit.diagnostics module to evaluate the performance of a forecasting model. It takes an already trained model as input and performs cross-validation on it. The initial equals 730 days parameter specifies that the first 2 years of data will be used for training the model. The period equals 180 days parameter indicates the frequency with which the training data set will be updated, effectively retraining the model every 6 months. Finally, the horizon equals 365 days parameter sets the forecast horizon to 1 year, meaning the model will predict values for the next 365 days after each retraining. The output, df_CV, is a data frame containing the cross-validation results, allowing for performance analysis of the model over the specified time frames. The df_CV.head function then displays the first few rows of this data frame, summarizing the results. This code imports the performance_metrics function from the fbprofit.diagnostics module, which is part of the Facebook Profit library used for time series forecasting. It then applies this function to a data frame named df_CV, which is likely containing cross-validation results from a profit model. The performance_metrics function computes performance metrics for the model's forecast, such as mean absolute error, root mean squared error, and others. Finally, the head method displays the first few rows of the resulting data frame df_p, allowing you to quickly see the computed performance metrics and assess how well the model performed on the cross-validation data. This code is using the plot_cross_validation_metric function from the fbprofit.plot module to visualize the performance of a forecasting model. The argument df_CV represents a data frame that contains cross-validation results, while metric equals MAPE specifies that the mean absolute percentage error, MAPE, should be used as the evaluation metric for the plot. The resulting figure, stored in the variable fig, will display how the MAPE changes over time, allowing you to assess the accuracy of the model's predictions across different periods. This code snippet imports specific packages from the IBM_Botocore and IBM_Boto 3 libraries, which are part of IBM's Cloud SDK for working with services like IBM Cloud Object Storage. The config class from IBM_botocore.client is typically used to configure clients for making requests to IBM Cloud services. The IBM_Boto3 library allows interaction with these services, likely for tasks such as uploading and retrieving files. Additionally, the OS module is imported, which provides a way to interact with the operating system, allowing access to environment variables and file system operations. The final line simply prints a message confirming that the packages have been successfully imported. This code snippet defines a dictionary called cos_credentials, which is intended to store various credentials and configuration details needed to access IBM Cloud Object Storage. The keys in this dictionary include IAM_service_ID, IBM_API_key_ID, ENDPOINT, IBM_AUTH_ENDPOINT, bucket, and file. Each of these keys corresponds to a specific piece of information required for authenticating and interacting with IBM's cloud storage service. It's important to note that before sharing this code, it's advisable to remove or obfuscate the actual credentials to maintain security and protect sensitive information. This code defines a function that uploads two data frames, df and df_future, as CSV files to IBM Cloud Object Storage, IBM COS. It takes credentials, the two data frames, and a tick parameter, which is used to name the files. First, it creates a client for the IBM COS service using the provided credentials, which include API key, service instance ID, authentication endpoint, and endpoint URL. The two data frames are then saved locally as CSV files named based on the tick parameter. Within a try-except block, the function attempts to upload both CSV files to a specified bucket in IBM COS. If successful, it prints a confirmation message. If any error occurs during the upload, it catches the exception and prints the error message. Finally, after a successful upload, the function deletes the local CSV files to clean up. This code snippet calls a function named upload_data_to_IBM_COS, which is responsible for uploading data to IBM Cloud Object Storage, IBM COS. The function takes four arguments, cos_credentials, which likely contains the necessary authentication details for accessing IBM COS data, presumably representing the primary dataset to be uploaded, future_data, which might contain additional or supplementary data, and the string IBM, probably indicating the target storage or a type designation. Essentially, this function facilitates moving both mined and modeled data into a cloud storage environment, ensuring that the data is securely stored and accessible for future use.